Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to Finite Element Methods. In the last class we have solved a one-dimensional bar problem using a polynomial trial function. So in the present class, let us do one more problem on that. So let us take different trial functions. Let us take a zero order trial function, first order, second order, and let us see what are the implications in choosing the trial functions in the Rayleigh-Ritz method. Let us take a bar, same problem, again with a body force. There is a body force, let us say that is Q, and that is given as Cx, it is varying with x, and there is a point load P which is acting at the right end, and on the left hand you are having a fixed support. Let the bar is having a length of 1 unit. So let us find out the exact solution for this first. Do we have exact solution for this? Yes, of course. So how do we find out the exact solution? Through the governing differential equation. So the governing equation for this bar problem is EA d square u by dx square plus Q equal to 0. So what is the highest order for this? It is of second order homogeneous ordinary differential equation. So that's why how many boundary conditions we need to solve this problem? We need two boundary conditions. So what are they? U at, if you assume this is the reference, okay? This fixed end is the reference. U at x is equal to 0, and on the right hand you are having a point load. So this can be written as EA du by dx at x is equal to L is P. Agree? So what is this EA du by dx? So E du by dx is your strain. So E multiplied by this grad u will give you stress multiplied by the area, you will get the force. So that is the same thing. So we are having a Neumann boundary condition on the right hand side precisely, and we are having a Dirichlet boundary condition on the left hand side. Good. So using these two boundary conditions, we have to solve this. We have to write the solution for this differential equation. All of you know how to write it. It is pretty straightforward, isn't it? So it can be written as EA d square u by dx square plus Q we assumed that as Cx equal to 0. That implies d square u by dx square is nothing but minus Cx by EA. Now integrating it with respect to x, now du by dx is nothing but minus Cx square by EA plus A, that is a constant. Now integrating it again, you will get the displacement u is equal to minus C x cube by 3EA plus AX plus B. So now in the solution we are having two unknowns A and B. So we are having two boundary conditions. So substitute those boundary conditions and get A and B. U at x is equal to 0 is 0. And what is our u? U is nothing but minus Cx cube by 3EA plus AX plus B. That implies at x is equal to 0, that is this is 0, this term is 0. The remaining thing is B equal to 0. This is from the first boundary condition. And the second boundary condition. What is the second boundary condition? EA du by dx at x is equal to L. That equal to EA. What is du by dx? Du by dx already we have it. Du by dx is nothing but minus Cx square by EA plus A. Again I did some silly mistake. It has to be Cx square by 2EA. It has to be Cx cube by 6EA. Integration, right? This is 6EA. This is 2EA. Okay. And this is at x is equal to L equal to P. That implies EA into minus C L square by 2EA plus A equal to P. But what is our L here? We assumed the length of the bar as 1 unit. That is, since here L equal to 1 unit, now it is EA into minus C by 2EA plus A equal to P. That implies minus C by 2EA plus A is nothing but P by EA. That implies A is nothing but P by EA plus C by 2EA. So this is the differential equation we need to solve, and d square u by dx square is nothing but minus cx by A. Now you are integrating it once. On the left hand side it will be du by dx. On the right hand side it is cx square by 2EA plus constant A. Now integrate it again. Now you will get u is equal to minus cx cube by 6EA plus ax plus b. So now we need to calculate two constants A and B. That we can calculate from the boundary conditions. So one boundary condition is Dirichlet boundary condition at x is equal to 0. That is, at x is equal to 0, the u value is 0. So that is why if you substitute x is equal to 0 in this expression, then you will get b as 0. Now the second boundary condition is the Neumann boundary condition. That is EA du by dx at x is equal to L. That is nothing but EA into du by dx. We have already calculated it. That is nothing but minus c x square by 2EA plus A. Put x is equal to L here, that is equal to P. So now x is equal to L. Here our length of the bar we assumed it as unity. So it will be minus C by 2EA plus A. So EA into minus C by 2EA plus A is equal to P. So minus C by 2EA plus A is equal to P by EA. So A is nothing but P by EA plus 2C by 2EA. Now the exact solution is u is equal to, what is the polynomial we got? Not polynomial, yeah. What is u? U is nothing but minus cx cube by 6EA plus p by EA into x plus cx by 2EA. Agree? So this is our displacement, the exact displacement. So you can make some more assumptions basically. If EA is equal to 1, so there is another name for this EA. This is called axial rigidity. So U is written as minus cx cube by 6 plus px by 1 plus cx by 2. Remember, what is P here? P is the point load at right end. What is C? C is involved in our distributed load. C into x by 2 minus x cube by 6 plus px. Now let us solve the same problem using Rayleigh-Ritz method. So what is the potential here? So pi p is written as half integral EA du by dx whole square into dx minus integral qu dx minus, you are having a point load also, p multiplied by u. So what is this u? U at x is equal to 1. This is u at x is equal to 1. Your point load is at the end point, or is the right end. That is u at x is equal to 1. So this is our potential. And what are the limits here? 0 to 1, 0 to 1. So what is this q? Q is your distributed load and u is the displacement, and dx So this is our potential. This we know how to write. Meaning we were writing only these two things, and in the last problem I have included the point load. So that point load concept also will come here. That point load is an external force basically. So that will come under the work potential thing. So now we need to solve this. So for this, what we need to do, we need to assume some trial functions. So let us assume a constant trial function. So let us assume a trial function as zero order trial function. So let u tilde equal to a naught, right? So if u tilde equal to a naught, then if you differentiate this, meaning we are having a du by dx term here, if you observe so before that, before substituting this one here, whatever the trial function you assume, what it has to do, it has to satisfy your essential boundary conditions. That is, what are the essential boundary conditions here? U at x is equal to 0 equal to 0. That implies, so u at x is equal to 0 equal to a naught equal to 0. That is, we are getting a naught as 0, which is a trivial solution. We don't want these type of solutions. So that's why this is not a good candidate for our function. Okay, this is not a good candidate at all. Now let us increase one more order. Second one. First order trial solution. So that is, u tilde is given as a naught plus a1x. Now this has to satisfy our boundary condition. So what is that? U at x is equal to 0 equal to 0. That implies, what will you get? A naught equal to 0. That is, I put x is equal to 0 here. This will be 0, so a naught is 0. So now what is the surviving thing? Our u tilde is nothing but a1x is our trial solution that satisfies the essential boundary conditions. Okay. So now we fulfill the first requirement, and what is the second thing? Now we have to substitute our trial function in our potential. So our potential pi p equal to half integral, just calculate this du tilde by dx also, that is nothing but a1. So this term is also there in our strain energy. So that's why calculate that one, that is a constant one. So strain is constant here. That is a pretty much very well known thing, because you have assumed displacement as a linear function, so your strain is nothing but the gradient of the displacement, so you will get a constant obviously. Good. Anyway, so it is pi p is nothing but 1 by 2 integral Ea du by dx whole square into dx minus integral qu dx minus p u at x is equal to 1, at x is equal to 1, u at x is equal to 1. So this is the work potential case, this is the strain energy case. Okay, so let us put u tilde everywhere. That is our trial function na? That's why. So upon substituting the things, pi p is given as half integral Ea du tilde by dx is nothing but a1, that is a1 square dx minus integral what is your q? Your q is nothing but c times x into u tilde dx. If you remember, this is cx, I have written in the first time itself, p into u tilde at x is equal to 1. Okay, so now what is this u tilde at x is equal to 1 is nothing but, so u tilde, that implies u tilde is equal to a1x, that implies u tilde at x is equal to 1 is equal to a1. That implies pi p equal to half integral Ea a1 square dx. Limits are important, 0 to 1. Limits are 0 to 1 minus integral cx into what is u tilde? U tilde is nothing but a1x. a1x square into dx. This is also from 0 to 1 minus p into u tilde is at x is equal to 1 is a1. So this can be written as half. If you assume this entire EA thing as unity, then it can be written as EA1 square by 2 integral 0 to 1 dx minus integral 0 to 1, this is CA1 into x square dx minus PA1. That implies pi p is nothing but EA1 square by 2 into, what is the first term? Integral 0 to 1 dx is nothing but x varies from 0 to 1 minus CA1 into, what is the second term? Second term is integral 0 to 1 x square dx. So what is the integral x square? It is x cube by 3, limits are from 0 to 1, minus PA1. So that implies EA1 square by 2, this value is 1, minus CA1 by 3 minus PA1. So now, according to Rayleigh's method, dou pi p by dou A1 equal to 0. Okay, that implies, this is, if you differentiate with respect to A1, it is 2A1 by 2, nothing but A1 minus, this is with respect to A1, C by 3 with respect to A1 minus P equal to 0. That implies the constant A1 is nothing but P plus C by 3. So the solution using linear trial function is u tilde is nothing but a1x, that equal to p plus c by 3 into x. So what is p here? P is the point load, c is a constant involved in your distributed load. Okay, so this is the solution. So if you are having u tilde, then you can calculate the strain also. My epsilon is nothing but dou u tilde by dou x, nothing but p plus c by 3. No wonder it's a constant. And what is stress? Stress is nothing but sigma is nothing but E times epsilon. If you assume linear isotropic elastic thing, elastic assumption, it will be E times epsilon. It will be E times p plus c by 3. This is your stress. It's just simple pull, na? This is 1D complete. So it is E into p plus c by 3. Quadratic trial function. So let us assume the trial function u tilde is nothing but a0 plus a1x plus a2x square. Okay, so now what you have to do, you have to substitute this one, that is, it has to satisfy the essential boundary conditions, right? That is the first requirement. So what are the essential boundary conditions? You are having it x is equal to 0, your u naught is 0, basically your displacement is 0. So if you do that, your a naught will become 0. A naught will become 0 from essential boundary condition, that is u at x is equal to 0 is 0. Okay, then you will left with u tilde is nothing but a1 x plus a2 x square. This is what you left with, a trial function that satisfies essential boundary conditions. Now what you have to do, you have to substitute this trial function in the potential, again what I did for the linear case. So do the same exercise, that is, our potential is nothing but 1 by 2 integral EA, if you assume this as unity, EA du by dx whole square into dx minus integral q u dx 0 to 1 minus P times U1. So this is the potential. Just substitute this U, that is, this is the U, you substitute here, then you will get the potential in terms of, so now pi P will be a function of A1 comma A2. You have to differentiate this pi P with respect to A1, this has to be 0, and dou pi P with respect to A2, this has to be 0. So you will get two simultaneous equations with unknowns as A1 and A2. Calculate them and get the displacement, get the strain, get the stress. So if you see your displacement, now here it will be quadratic and strain will be linear. That is, you are increasing one more order, so you are fitting the displacement with some more accuracy, some more accurate polynomial basically. So obviously the solution will approach your exact solution. That is, if you increase the number of terms, obviously you will approach the exact solution. So this is one way of doing, meaning which trial function you have to choose basically. So the trial function must satisfy the essential boundary conditions as well as just see the order of the equation. What is the highest order in your potential? So based on that also you have to consider your trial function. Not only on the essential boundary conditions, you have to see the highest order in your potential also. You cannot ignore that. Otherwise you get some trivial solutions which are useless basically. So that is why one need to be careful while dealing with these things. What trial function I have to choose? Basically the reason why we choose the polynomials or the sinusoidal functions are, so basically sinusoidal functions are much more very comfortable, because how many times you differentiate them, there won't be any discontinuity, they are always continuous. So whatever the highest order of the differential equation you are having, highest order you are having in your potential, so that you can easily handle with the sinusoidal functions. That is the beauty of sinusoidal functions, but you have to deal with sine, cosine products and all there, and even that can be easy since you are dealing with the trigonometric functions, orthogonal functions when they are orthogonal. So using the orthogonal property, if you exploit that property, even you can solve those sinusoidal functions very easily. And these trial functions which are in the polynomial form, polynomial trial functions, also very easy. You need to do some more exercise, meaning some algebra we need to do even in these things. So this is how we will apply the Rayleigh-Ritz method using polynomial trial functions. So in the next class, let us compare a Galerkin method and a exact solution and the Rayleigh-Ritz method, all three combined. Let us see whether that will give the same result or not in the next class. Let us apply that to some small differential equation. Let us test whether these methods are giving us the correct results or not. Thank you so much for watching this video. Stay tuned to Ekeeda, subscribe to Ekeeda.